Imagine 100,000 people packed shoulder to shoulder, staring up as the night sky explodes with brilliant color, each firework seemingly blooming at the perfect moment in perfect harmony with the rest. What you're witnessing isn't just artistry. It's the result of meticulous engineering, centuries of chemical experimentation, and timing as precise as a Swiss watch. But how do fireworks engineers choreograph all this, transforming gunpowder and metal salts into beauty and spectacle high above? Let's break down what actually happens from the moment a firework leaves the ground, because each sparkle and burst is no accident. Picture a classic Peony firework. That's one of those vivid spheres of color that radiate out and fade evenly. The timing of its ascent, explosion, color, and even the arrangement of individual bursts inside are all painstakingly engineered. The secret starts inside the cylindrical shell, sometimes no bigger than a grapefruit. At its core is a small but powerful charge called the lift powder, a tightly packed black powder that acts just like a mini rocket booster. This is what launches the firework into the air with impressive force. Timed perfectly with the launch is a fuse made of tightly wound paper or string coated in slow-burning chemicals. The intricacy here is striking. As the fuse burns, it measures the seconds the shell spends arcing upward, counting down so that the main charge inside detonates at exactly the right altitude. Think of it as a primitive but highly reliable timer. Now, let's zoom in. Nestled inside the shell are small pellets called stars. Each star is a tiny chemistry experiment, a blend of specific metal salts and a fuel. For example, strontium compounds turn crimson, copper salts glow blue, sodium compounds radiate yellow, and barium salts produce green. By changing the chemistry of these stars, engineers determine the colors that will paint the sky. But color and timing alone aren't enough. The arrangement of the stars within the shell is another art. If the pellets are clustered tightly around the central bursting charge, you'll get a tight, dazzling sphere. Arrange them in a ring, you get a ring in the sky. Some shells contain multiple layers of stars or compartments separated by thin disks, allowing for a sequence of bursts. Think of those fireworks that explode, pause, and then bloom again in another color. Each delay, each layer, is a calculated difference in chemical burn rate or physical placement, all carefully engineered in advance. So when an audience gasps as a firework erupts in red, and then, moments later, unveils a cascading blue willow, they're really seeing the result of engineers controlling two seemingly wild forces, chemistry and time. Not to mention manipulating gravity, pressure, and airflow all at once. Think about the nature of the timed fuse for a moment. Early firework makers relied on nothing more than hand-rolled tubes, estimating burn rates by trial and error. It was an imprecise and occasionally dangerous science. Modern shells may use precisely measured fuse compositions to regulate burn rate down to tenths of a second. Sometimes digital timing modules or electronic ignition systems are included in larger shows, allowing experts to synchronize fireworks with musical scores, every crackle and bloom matching a crescendo or drum beat. Context makes this even more impressive. Fireworks weren't always these rhythmic ballets of light. In medieval China over 1,000 years ago, the first fireworks were little more than crude bamboo sticks filled with black powder. Their timing was anything but precise. Over centuries, artisans experimented, learning how to refine powder grains, shape fuses, and track altitude, driving the art ever closer to science. A modern fireworks display is less like lighting a string of firecrackers and more like orchestrating a symphony, each chemical instrument coming in exactly when the conductor wants. Sophisticated computer programs today simulate burst shapes, drift, and even wind, letting engineers predict what the audience will see from the ground well before any fuse is lit. Yet, the drama of a firework as it unfolds overhead remains something that feels almost primal. Dazzling patterns choreographed against the randomness of wind and weather, controlled by human hands from the ground. Let's reflect on a poetic description that seems to capture why fireworks matter beyond just technical achievement. With blazing flowers, we break the dark. A burst of color, a fleeting spark engineered with measured art. We light the sky, then drift apart. That fleeting nature is part of the magic. Every burst is designed to be both perfectly timed and perfectly temporary. There's no undo button, no way to replay the spectacle. The plan must be flawless, the engineering invisible to the audience. That might be the true test of mastery. If you look closer, you'll see that timing mechanisms in fireworks work on very simple principles. Heat from the burning fuse travels along a calculated path, igniting charges in sequence. In the case of multi-break shells, the kind that burst, pause, and then burst again, each compartment is separated by a layer of timing fuse with a slightly slower or faster burn rate. Sometimes delays are engineered by packing clay or other non-flammable barriers, forcing the fire to wait before it reaches the next compartment. It's not just about delay, though. Timing is crucial for safety as well. Imagine a shell bursting before it's reached its intended altitude. The results could be catastrophic. That's why engineers conduct test launches, use precise measuring tools to calibrate fuse compositions and standardize every variable they can. Temperature, humidity, even grain size of the powders. The chemistry of color is just as precise, almost like tuning a palette of light. A small impurity, a droplet of moisture, or a wrongly measured compound, and a planned blue could fizzle disappointingly into gray. To create pure, stable colors, manufacturers purify salts, control environmental conditions, and research new compounds, always searching for both effect and safety. Some colors, like blue, remain notoriously difficult to perfect. Reliable blue fireworks took centuries longer than red or green, simply because the right copper compounds that burned with an intense blue were harder to produce and stabilize at the required temperatures. Shape and motion get even more interesting. Engineers use microstructures like tightly wrapped tubes or star pellets arranged in spirals to force stars outwards in particular shapes: rings, smiley faces, or hearts. Each arrangement must survive enormous acceleration from launch and then detonate with perfect symmetry. Any miscalculation, and the pattern distorts beyond recognition. Ever wonder how those enormous finale effects work? Where the sky seems to pulse with fire. That's usually the work of electronically synchronized shells, each triggered remotely, milliseconds apart. Operators use computers to ignite electric matches instead of fuses, overcoming the historical challenge of fuse variability. It's an awe-inspiring application of digital technology to a centuries-old tradition. But firework engineering doesn't stop at spectacle. There's a constant and often invisible quest for greater safety, better environmental responsibility, and more ambitious displays. Researchers experiment with new green pyrotechnics, using nitrogen-based compounds instead of heavy metals for less pollution, seeking alternatives that produce vivid color without toxic byproducts. Now, pause and consider why this all matters. Fireworks are ephemeral. They burn, fade, and vanish in seconds. Yet, for those few seconds, they turn human effort and inventive spirit into something that can only be seen, never touched, and never recreated exactly the same way again. In that sense, engineering a firework is a tribute to both precision and impermanence. a controlled blaze of light and sound, trusting that the sum of meticulous details will add up to awe. The next time you watch a firework arch into the night, remember, it's exactly where it needs to be, exactly when it needs to be there, and exactly the color it was always intended to be. From the moment a technician loads a shell onto its mortar, to the instant its pyrotechnic heart splits open the sky, everything has been planned, engineered, and rehearsed until there's almost no room left for chance. And for those who make them, the challenge never truly ends, because every show is a question. Can human hands measure, anticipate, and guide the wild dance of chemistry and physics overhead? So far, the answer is yes, and each new firework offers proof, in one brief explosion after another. When a firework is prepared for launch, technicians load the shell into a mortar tube, taking care to line up the fuse with an electric match or timed ignition system. The area must be clear and safety protocols strictly followed. As the system is triggered, a current fires the electric match or ignites the traditional fuse, setting off the lift charge. The shell shoots skyward with a deep, echoing thump, trailing sparks from its base and leaving a glowing arc through the night. As the shell arcs upward, the internal fuse burns at a predetermined rate. This timing must match the calculated ascent, so that the shell reaches optimal altitude before the main charge detonates, ensuring the explosion is both safe and maximally visible. At the apex of its arc, the burning fuse ignites the main charge. The shell's casing bursts open, launching burning stars outward in a perfectly calculated spherical pattern. Each star ignites its respective color as it arcs outward from the center. Each star, depending on its initial placement and chemical composition, burns with a specific color and follows a unique trajectory. This creates the desired visual effect in the sky, from tight spheres to scattered willows or changing colors. If the shell contains separate compartments or layers, a timed fuse or clay delay ensures that each section bursts in order. That's how you get a sequence: an initial red bloom followed seconds later by a blue willow, or a ring morphing into a sphere. Engineers can design a shell to create hundreds of variations: peonies, chrysanthemums, willows, rings, and smiley faces, each with unique star placement and timing. Modern techniques allow for tight control over burn rate and symmetry. The end result blends showmanship and strict engineering. Designers must predict the impact of wind, varying humidity, and subtle changes in powder composition, running simulations and countless small-scale tests to ensure every burst is both beautiful and safe. Once a design is approved, technicians conduct repeated test launches in controlled conditions. Every aspect is calibrated: fuse burn rates, powder consistency, and shell mass, using measuring tools and observation from multiple vantage points for data collection. At major events, advanced synchronization systems allow fireworks to align with music, with computers converting musical cues into timing signals for ignition. Every burst, pause, and crackle can match the melody and rhythm, turning the sky into a canvas for sound. Operators constantly monitor wind speed and weather, making adjustments on the fly. Launch angles, shell selection, or even firing order can change minutes before showtime to compensate for shifting conditions. Immediately before the show, every shell receives a last inspection. Technicians double-check fuses, confirm digital sequencing, and inspect the mortar alignment, using checklists and redundant systems to ensure safety and perfect execution. For the audience, the show is a sensory experience. Visual splendor, chest-thumping sound, and communal awe, all orchestrated by careful, unseen hands. It's the sudden silence of anticipation, the dazzling explosion, and the rolling cheer that follows. Despite all preparation, there is always an element of chance. wind shifts, a powder variance, or a fuse burning a fraction faster or slower than tested. True mastery is making beauty despite the variables. Every fireworks show is both a continuation of an ancient craft and the boundary of new science. New compositions, digitally enhanced choreography, and environmental innovations push the art form further each year. In the end, fireworks combine math, chemistry, artistry, and risk. A flash of order against chaos, as brief as it is unforgettable.